Here we are, guys, at one of our condensing units at the office. And as you can see, we're here at our electrical panel. And some of the common joys of being a technician. As you can see, I have to be extremely careful with our copper lines going here. And I've got about a foot of space. So yeah, installers don't really think about technicians a lot when this happens. But what we're looking at here is we're looking at our electrical in the unit and our contactor. Now some units, they're not going to have these because it's going to be have a control board. Like this ream unit next to me actually does not have a contactor because of the board that's in it. This is typically what you will find in most AC units, single stage. So we have our hard start capacitor there with its relay. And then our contactor. Now I have the power on, so I'm gonna make sure I don't electrocute myself here. But this is our contactor right here. Some of you'll see an exposed button or buttons in the center, as this is a 2-pole, so there's a 2-pole break in the center where the switch is. So when we're testing this to see if it's good, once I get my meter on here, I can show you exactly what we're looking for on startup and what it's going to do when it is off. What we're going to be checking, the very first thing is we want to make sure it is not connected on startup. Now when it's a relay like this, it should not be closed on startup. You should not have continuity between this pole to this pole. So it should be open when we check it. So we're going to flip our meter here to the continuity symbol. And we should not hear that beep when the thermostat is not calling for cooling. So as we can see, we are going to get a kind of beeping when the power is on, because you're going to get some kind of interference, which is why when you're first checking for it, make sure that you pull the disconnect when you're checking for continuity. Okay, there we go. So now while we're checking between these poles, they are not closed. Okay. So when you go to turn on the unit, you push your disconnect back in or you turn your toggle on, use extreme caution when you're testing to make sure that you are getting your 240 volts in here at the bottom where the power is coming in from your disconnect to the unit. And also make sure that you are getting your 240 volts here, which is going into your unit. So once you've established that you do in fact have 240 volts coming into your contactor and you are not getting 240 volts out, one of two things is happening here. So you're either not getting your call from the thermostat. So here on each side is your 24 volts. That is the control voltage or the low side voltage rather, coming in from the thermostat to tell your unit to come on. So that control voltage, what it's going to do is it's going to pull that in so that you make a mechanical connection and the 240 volts now can go through into the unit. So now that we know we're getting power here, we check to make sure that we are in fact getting 24 volts here and here to make sure that, that 24 volts is actually being sent out to the unit. So at that point, you're going to change your meter here to volts AC. since in this application it is using AC voltage. And again, you're going to put one lead on each side, and which I'll show you in the bench. But I can show you in detail what it is we're going to look for when we pull this out or when we're testing it at the unit. If you are in fact not getting your 24 volts to your contactor here, and again, do not test against ground. Now that our unit is on, we're going to check for voltage here. And again, use extreme caution when touching any electrical. Okay, yes, we are now currently reading 26.3 volts, which is perfectly normal. Do not test against ground. Always make sure you have one lead on each terminal when you are checking. As I mentioned before, when we want to check for our 240 volts in, you need to make sure that power is getting to the unit. And it's hard to hear over the unit here, but there's our 242 volts, so our 240 in. And then if it is making the correct connection, you should be getting 240 volts out. So if you know that you are in fact getting 240 in, and if you are able to push your contactor in here at the switch, which again we'll show more in detail at the bench, then you know that your contactor is making contact like it should, and you probably don't have your 24 volts coming out to the unit. Once we've established at least that much, knowing that we are getting power to the unit at 240 to 244 volts, we know that it has something to do with the contactor itself, or it has to do with the control voltage coming in to the contactor. Now, the reason why we're going to check for voltage first is there's a chance that you just might not be getting your high side power coming in from your disconnect. What you would do at that point is you would trace it back to your disconnect, and you'll know where your disconnect is. You're going to have a piece of conduit coming in where your electrical wire is going to be bundled into, and then that's going to be going back to your disconnect. You'll have a disconnect box. But you know, I just wanted to show you guys what it is you're looking at, because it's hard to understand just from seeing it at a bench, at the testing parts bench, because they're all not going to look the same, right? So let's go back inside and I can go ahead and show you how it is we're going to be exactly testing for that voltage at your contactor. All right, so some of you might have a disconnect that looks kind of like a breaker. A lot of disconnects are going to look similar to this, and as you can see, this one has an on-off switch here, kind of like a breaker. So you might have one of those, or yours might have a pull-out style connection. Make sure I turned both of those back on. So when you are going to test it at first, make sure you do turn the power off before going ahead and checking and making sure that you do have your 240 volts. So the reason that you want to pull the power first is just so you can check across on continuity and make sure that the lines are not actually closed or the relay is stuck. Because if your relay is stuck, obviously it shouldn't be doing that. It should be open, and you should not have continuity when you're not calling for cooling on the unit. So if you do have continuity on the contactor before you've even turned the contactor on, not making that connection, you know that the relay is stuck and therefore your contactor is bad. But for everything else, you're going to make sure that you do have your disconnect turned on, pushed in if you have one of those pull-out style connectors. And then that's where we're going to cautiously check for power. Anyway, let's go back inside and let's bench test our contactor so we can see what I'm talking about. Okay, so just so you can see how this functions, and I'll pop this up on the screen here in just a moment. What we're looking at here is how your contactor works when you energize the coil here, which you can't see. It's actually here. This is your 24-volt coil. Inside of this, all these neat little things here, this design, and this is called an electromagnetic mechanism. Just like a transformer, if you watched that video, we kind of broke it down, how a transformer functions, and also how a normal permanent split capacitor or PSC motor works. This one has the same mechanism as far as the electromagnetic mechanism. These are your contact points, and with a 2-pole contactor, it means both of these circuits are normally open. This means there is not a constant contact like you would have with a single pole contactor. And let me show you what that looks like. Okay, and this is our single pole contactor. So if we zoom in just a little bit here, you can see that it has a solid leg or a solid pole. And what that means is there's going to be a constant 120 coming through here. Underneath this protective plate, like the 2-pole, it's going to have this normally open hole under here. So with single pole contactors, you will always have that 120 here active, and this needs to close in order to make the contacts connect once it's got energized, and that allows the 240 volts through to turn on your AC. So how does all this work? Well, here, what we're calling our control voltage is our 24 volts AC, which we'll get into in a moment, but this sort of breaks it down for you, what it looks like, what we're looking at here, something tangible, you know? So here is our control voltage, and control means this is the voltage needed to energize the magnet in order to make contact, that mechanical connection, to allow all of that voltage through. So here, these are called contact points, and they're kind of hard to see. Let me see if I can grab a screwdriver here, see if I can pull these back just a little bit for you. Get one of my little guys. And just under here, there is contact point. And since this is a new one, you can kind of barely see it right there. Since this is a new one, it's not going to be pitted because it hasn't had enough time to arc and burn. So there is an arc here, which as this ages, these are going to become more and more pitted on those points, which is why they end up going bad. So I recommend replacing these once, really every 5 years, just as preventative maintenance. So you're not having to go out, rush out last minute and, nothing's coming on outside and this guy's your culprit. So I'd recommend once every, 5 years-ish, just take a look at your contact points under there and definitely have a good idea. Technicians, this is something to look at. And as we'll get into in a moment, you need to make sure you are getting low resistance across your pole once it does connect. So this spring is going to pull in closed because of this electromagnetic mechanism here, which the coil energizes, that is wrapped around this iron core. Now here's your moving iron core up here. These are actually separated. So when this becomes energized, it's going to pull that in, that spring is going to be pulled down, and these contact points are going to make a solid connection across. So your voltage coming in from your home, from your main breaker in the home, that's going to come in, this is going to close, and then you should get that voltage out. This is a 24 volt coil, meaning it's going to operate and energize on 24 volts AC. As we'll get into in a moment, just trying to repeat this knowledge, really work it in. This is what we call control voltage. It comes in from your thermostat to pull and make this connection so the unit comes on when you are calling for cooling. So this gives you an idea of exactly what this is doing when it does receive that 24 volts coming in and how it functions. Now, a lot of people have an exposed coil here. So underneath this plastic is this copper winding, this coil. If this is exposed, you're going to see burning here. And once that coil burns, it's definitely bad. If you see obvious signs of burning here, or obvious signs of burning here where your quick connects are going to come in, or your lugs, I would definitely replace that just so you're being safe for you and your family. So now let's get over to the other part of the video where we're going to connect the power up, and we get a little more in depth on this. This is more than likely closer to what you're seeing out there with these exposed connections like this. Again, since these are not pushed in, they're not closing that circuit across, you should not have continuity when going across here. As you can see, it is not beeping, and it should not be beeping until we get that control voltage closing the circuit here. And as you can hear that, when you're out there, you should see that this pulls in when the thermostat is calling for cooling. The 24 volts should be coming out. Now remember, a lot of times there's a delay. It depends on the thermostat, if it's programmed. There's certain smart thermostats that have a built-in delay. But just keep in mind, it might not kick on right away. There might be a bit of delay. However, you should see this pull in. So if you are seeing that this is pulling in like that, you do have your 24 volts. If this is not pulling in, you do not have your 24 volts. Now, there is some exception here. It's really hard to see, but right in here, in this area, there's a teeny tiny coil, that copper coil there. And if that gets burned or severed, something like that, then If you are getting 24 volts and it's not pulling in, your contactor might actually be bad, or one of the copper connections came loose. So that's also why it's important when you're out there to check for your volts and make sure that you are in fact getting your 24 volts. This way we know 100% you are getting voltage. So if you are getting 24 volts here and this is not pulling in, we know it has something to do with the contactor, whether it be the coil, you know, something along those lines, because you know that you are getting volts, your voltage here. You can rule that this is bad. You are seeing that this is pulling in and nothing is still coming on. At that point, we need to know if we are getting our 240 volts. So you would check across here on this side coming in. Remember, one lead on each pole. We're not checking like this. We are checking like this, okay, to make sure. So here, with our 24 volts that has pulled this in, we can check and make sure that we are getting our continuity across. Help if I had it on the right setting there. Okay, we're getting low resistance and it is making connection. So you can do it this way, just to check and make sure you are getting low resistance on your contact points. And it's good to check that anyway, because every time this pulls in, it's going to arc and burn, which means just under here, those plates are going to get pitted, and eventually they're not going to make good connection. So now that we know we've got our 24 volts, this is pulling in, and we do have continuity, we need to make sure that you have high side power. So you're going to have high side power coming in from your home through the disconnect box that comes in from that conduit, and that you should see some metal pipe. And so this is simulating that high side power that's going to be coming in here. We are calling for cooling. So we're going to check for 240 volts coming in, our power. And again, it would help if I switch the settings over here. All right. There it is. We know we're getting 240 in. And then on the other side of those poles there, we are getting 240 volts out. Now you can check here if you want, or here. I just like to check here at the direct connection coming in. If you are getting 240 volts in, but not out, your contactor is bad. Keep it in mind, however, you do have to have those 24 volts, and that's the first thing to check for. When you come out to your contactor, make sure that you are getting 24 volts. Your thermostat has to be turned to cooling in order for you to check for your low side power. So once you've established you do have 24 volts, at that point it's finding out if you do have your 240 in, it is making a good solid connection, and you have 240 out. If you have both of those things, at that point I would move on to your capacitor, or for those that have defrost boards, you might want to look at that as far as your heat pump is concerned. Some single stage straight cool condensers do have pressure switches out there, so that could be something else going on. But we'll get into that later. For now, this is how you're going to check your contactor and what a contactor does. So now you know, and you know how to check that. Now, for instances like these, you don't have to have a clamp meter like this. You can just have a multimeter. But as a homeowner, it's a really good idea to have something if you're wanting to fix or repair your own units. You want to make sure that you have something that could read amps so you can check your amp draw if anything else goes wrong in your home. It's just a good thing to have. And as I was mentioning before with our capacitor videos, when we were testing those, you don't have to have a fancy meter like this that also reads microfarad. And even those you can find less expensive at places like Harbor Freight. Home Depot carries some, Lowe's carries some. Just something that is a multimeter that can read, all your basic stuff: volts AC, volts DC, amp draw, continuity, ohms. This one right here is diode. And then, of course, your temperature. So once you hit that point of home ownership where you're needing to repair your own things, or if you're also a property owner or multifamily management or owner, these are really good things to know, or things for your guys to know and understand, because it's going to save a lot of money. So I highly recommend getting at least a multimeter, even better if you can get a clamp meter. This is definitely going to save you a lot of time and a lot of money. So thank you so much for joining. Once again, thank you so much for joining me today. And if you have any questions, just leave them in the comments below and I will get to them as soon as possible. If you want to watch more videos like these, just hit the subscribe and do us a favor and give us a like so we can get more information out there to homeowners and technicians like you. Thank you so much again and have a wonderful day.